For the second half of LT2, we're going to revisit allele frequencies, which is dealing with the Hardy-Weinberg equilibrium. So if you remember, P plus Q equals 1, and P squared plus 2PQ plus Q squared equals 1. So with allelic frequencies, we're just looking at how often the allele, so dominant or recessive, occurs in the gene pool. You should remember that populations evolve, not individuals. So natural selection acts on individuals, leading to the evolution of populations. So remember that variation has to exist within a population, and then the environment selects individuals based on their fitness. And then because of that, the genetic makeup of a population can change over time due to individuals being selected for or against. And so those with greater fitness become more common, while those with less fitness become less common. And so you start to see an evolution occur, and then over many generations you might end up with different species. So a gene pool is a collection of all the alleles within a given population. And so alleles are the versions of a gene, and a gene is a trait. So if the trait is hair color, then your alleles would be brown, black, red, blonde. And then your allele frequency is how common that allele is present in the population. So how many dominant versus recessive in the entire population. So we've seen this when we've talked about genetics and Hardy-Weinberg. So you have to have variation for populations to evolve, and variation can come from mutation, from gene flow, genetic drift, non-random mating, and then selection. So just as a refresher, mutations are changes in DNA that result in a new functional trait, and remember they can be beneficial, harmful, or have no effect. Gene flow is when you add or eliminate alleles due to immigration, whether that be the immigration of individuals moving into a population or individuals leaving a population. Genetic drift is the change in allele frequencies due to chance, because some individuals will reproduce more, some will die and not have the ability to reproduce, so this is just a natural drift. Non-random mating also gives variation, so the opportunity to mate is not left up to chance, so you see mate selection occurring. And then we know natural selection also allows for variation because those who are better suited or more fit will be selected for by the environment. They live longer, they produce offspring, whereas those who are less fit do not produce offspring or as many offspring. So bottleneck effect is when you see genetic drift, and this can be due to something like a catastrophe. So you have like a volcano or an earthquake, or populations getting separated due to a hurricane. So the original population, there's a lot of variation, and then those who end up surviving, there's less variation, and so your genetic drift drifts towards a certain phenotype. You can also have the founder effect. So the founder effect is when you have a population get separated, and so the founder group is small, and the new population will only have the traits of those founders. So there's low genetic variation within that area. To measure allele frequency, we use Hardy-Weinberg equilibrium, and so with that we have an unchanging frequency. And so if we see frequency changing, then we can assume that there are some evolutionary forces at play, and then we can see what forces there are. So remember, these are the equations for Hardy-Weinberg. For Hardy-Weinberg to occur, which it doesn't actually occur in real life because there's too many factors that come into play, but let's say it does, you would have no selection, so natural selection doesn't occur. There's no mutations, there's no migration, so no populations or individuals are moving in or out. You have a very large population, and there's always random mating. So for this problem, remember that P plus Q equals 1, P squared plus 2PQ plus Q squared equals 1. You always solve with the recessive, so you would say 340 divided by 2,359. That gives you a frequency of 14%, and that's just q squared. So we would get the square root of q squared, which is 0.38, and that gives us q. And then since we have q, we can solve for p. P is 0.62. And then you square that to get p squared, which is 0.38, and then 2pq for heterozygous. And then for 2017, you would do the same thing again, where you get q squared, 773 divided by 1989. That gives you q squared, get the square root for q, solve for p, and then you can solve for the rest. If it does meet Hardy-Weinberg, then the p and q would be the same. If it doesn't, then you would see a difference. So now for the rest of class, you're just going to work on examples of how to solve for Hardy-Weinberg, which is just review because we've done it before.